everyone. Thank you so much for joining us today. Before we kick this off, I do want to point out to the audience that we welcome questions. Please post them in the Q&A section at the bottom of your screen, and we will address those questions at the end of the presentation. So I'd now like to turn this over to Stephen Saltstein, Force Family Office's CEO.
Thank you, Callie, and thank you everyone for joining us today. As everyone just heard, Excel's solution is abundant. It's non-toxic commodity chemicals. It can deliver, up to 250 hours as of now for energy storage with a lifespan of over 20 years. I mean, it is a incredible option. And not to steal any thunder, let me just turn it over. It's my great pleasure to welcome Tom Sisto and Jeffrey Schwartz from Excel Batteries. Thank you.
All right, thanks, Steve. I appreciate the kind introduction. And thank you, everybody, for joining. Excited today to talk about the opportunity that we are presenting in Excel Batteries, which is an organic flow battery for the lowest cost utility scale energy storage. Okay, so I kind of wanted to just start with a summary of why this opportunity and this moment is really important for Excel and really exciting. And we've reached an inflection point, and we're moving from technical demonstrations, which I've shown on the right here. We put a unit into customers' hands that was a really powerful technical validation and moving into commercial product for these active customers. And so that's a really exciting time for us. We have what we believe to be the lowest cost energy storage for $1 trillion plus market. We've got $1 billion customer pipeline that we're actively developing and continuing to add to, which sort of showcases the need for this technology. We have deep IP protection. And then I think what's really interesting about us as a battery company and a utility scale industrial company is that we can be exceptionally capital light because this technology exists. It exists at grid scale. We're changing the chemistry within the technology. And so that's a really unique and interesting opportunity. So yeah, excited to sort of touch on all of those going forward. So I'll sort of start with the why problem. And it's the fact that the grid is aging and becoming very unstable. So as Stephen kind of alluded to earlier, if you happen to be in early into the waiting room, there's a huge amount of electricity usage in terms of growth. And so essentially, AI and industrial electrification are driving a huge new demand for electricity generation and consumption. And what's interesting is the grid is really complex as an industrial machine, if you will. It's one of the most complex machines on Earth, but it's also exceptionally old. And so assets are aging and breaking, and we're starting to see the cracks with blackouts. I know in New York about 3 weeks ago, there were blackouts due to the heat waves. So on and so forth. And then that's a really big opportunity because we're at a moment in time where we're going to be sort of reinventing the grid and modernizing it. And that's a $4 trillion opportunity just for storage alone. And so lithium ion is just too expensive. It's also very flammable, which is a huge problem for these multi-$100 million installations. And then other emerging technologies in storage are either too expensive, inefficient, or both. And so our solution is a wonderful solution to address those challenges and address this opportunity. So to kind of give a singular summary of one use case, and there are a myriad of use cases for utility energy scale storage, I'll just highlight one that's a very simple one, and it's California and sort of the penetration of renewables. Right. And so the reason that we need longer duration than lithium is capable of providing, lithium hits a wall at about 4 to 6 hours from an economic standpoint, is because essentially as assets are aging out, gas generation is aging out, we're faced with a question of, are we replacing these old assets with new gas plants that are very expensive and exceptionally long life? Given the fact that we're transitioning to renewables, which are the least expensive type of generation. And so we're faced with this decision. And what you can see is in California in 2020, the green line is batteries. They're essentially non-existent. Solar comes up at about 6 to 7 a.m. It peaks for about 10 hours, and then it starts to come down. And this light blue line is gas generation. And you can see this is the time when everybody gets home, everybody's cooking, air conditioners are running, People are consuming the most amount of electricity, and gas generation comes up as solar tails down. And then what you can see is in 5 years, there's been a massive amount of battery installation, and they're charging throughout the day. And then there's about 6 hours where they've come in and they've replaced the most expensive portion of time for gas generation, which is this peak demand. And so they're coming in and they're providing about 6 hours. But if we want to get rid of this gas, and or if we don't want to have to replace the really expensive assets as they age out, this is much longer than 6 hours. And so we're going to need longer duration storage that's an alternative to lithium because it's just not capable of filling this gap. And so that's a huge opportunity. With that, we've partnered with some various consultancy groups that model the grid for utility planners. So for instance, this is California. E3 is the consultant that does CAISO and other major utilities. And when we looked at what our asset could provide to California, using the tool that California uses to plan their grid for purchasing, $28 billion worth of our batteries were selected alongside lithium ion in order to enable renewables such as solar and wind. And in doing so, it provides $20 billion worth of savings for the ratepayers. So it's a win-win, and it's because we can be efficient and we can replace these existing assets that are aging out with a lower cost alternative. And if you extrapolate California's percentage of electricity usage out to a total global electricity usage, that would be $1 trillion market share just for us. So with that, what our technology is a flow battery. And flow batteries are really unique in that they're already scaled and already very mature. It's a 50-year-old type of battery, and it's already among the world's largest. They're just too expensive. And so the reason you've probably never heard of one is for that exact reason. They're just too expensive. And so they only fit into corner edge cases. And the reason why is that it's vanadium metal is the metal that's used to store the electricity, and that's expensive. And it only dissolves in sulfuric acid, which is very corrosive and drives a lot of costs within the system perspective. And so what a flow battery is it's two tanks. It's a positive tank and a negative tank. There's a charged storage material. In vanadium's case, it's vanadium metal, dissolved into a liquid put into the tank that's pumped through an electrochemical cell. And so that's very similar to a car where you have an engine and a gas tank. And so what's interesting is that you can lever those independently. If you want to take your gas tank on your car and take it from 10 gallons to 20 gallons, you can do that without changing the engine. And in doing so, you can now drive twice as far. And so it's a really powerful architecture of battery in order to get out to longer durations, which lithium or other pack types of batteries are unable to do. And so what we do is we leverage that really scaled, highly mature technology, and we replace the liquid that's inside the tanks. And so we use commodity organic molecule feedstocks to make from abundant petrochemical feedstocks our proprietary chemistry. We dissolve it into pH neutral water, and those are the charged storage materials. And with that, we're able to replace all the corrosivity and cost that drives within this system. And so we have the lowest cost of energy storage at a system level perspective because we can use basic plastics and rubbers, as well as our low cost proprietary electrolyte. So this was discovered at Columbia University, and it's essentially sourced, as I had mentioned, from the least expensive and most abundant commodity feedstocks. We transform that into our electrolyte, which has, as Stephen had mentioned, over a 20-year lifetime. And so with that, it's domestically sourceable, it's globally sourceable, it's safe, it's non-flammable because it's water-based, it's non-toxic, and it has a very, very long lifetime. We've deployed this, so we've deployed it with a customer, a demonstration unit. And what's interesting about that is that we've been able to run in the field all of the use cases that are industry standard for utility scale energy storage. So this is a fully integrated system. It's able to stand alone. It's got the chemistry, the hardware, sensors, controls, software, everything inside the shipping container. And then with that, we've been able to demonstrate that we can do both the fast response aspects for grid stability, as well as the long duration power backup use cases. And so one technology can do everything asked at the utility level. And so that's a very important thing because we can provide with a single piece of technology all of the customer needs, and they don't need to pair together many different technologies in order to uh, source their electricity needs. With that, we can also be a very flexible duration because it's just tank size is the dictation of the duration, and that provides the customer the lowest cost necessary to meet their needs. We expect to be 2 times less cost than lithium, both from a capex and then from a lifetime ownership cost. We're field proven to be essentially a match for lithium's performance while being able to do it for longer, and we're non-flammable, which is really important for industrial siting, and I'll sort of talk about that in a bit. And so with that, we can provide the lowest electricity price available. So we have a billion-dollar project pipeline, specifically driven today by non-flammability. I'll touch on that. We are not specifically the non-flammable battery. It's just a key wedge for us today and an important thing going forward as well. And so with that, we have a module to project qualification program that we have 2 customers for, and one is an AI hyperscaler, data center developer, and then the other is a petrochemical storage and shipping company. And so both of them are driven by a need for today, this non-flammable type of storage. From the AI data center perspective, it's going to be a $10 billion building full of NVIDIA and other AI chips. It's 1, very expensive, and 2, essentially irreplaceable. And so from an insurance perspective, they're unable to use lithium ion for the use cases that they want us for. And because of that, they need an alternative. They need it to be a fast response alternative, which we're capable of doing, and they need it to be non-flammable. For Stolthaven, which is a petrochemical storage and shipping company, it's also driven by non-flammability because the petrochemical industry has a big sensitivity to that. And so these 2 customers, because of their key needs today, provide a path to bankability and widespread adoption. And so essentially these 2 verticals, the petrochemicals industry and then the data center industry, they're massive in and of themselves. The chemicals industry as a whole uses 23% of US electricity. Data centers are expected to use 1 out of every 10 electrons by 2030, and electricity can be a massive operating cost for them. They have huge power demands and a sensitivity to flammability. With that, through deployments at the project level, we can become bankable as a technology, which leads to project financing and ubiquity across utility and heavy industries. So essentially, if you think of us similar to solar and wind at the project level, bankability provides ubiquity into utilities. And so with these 2 customers, we have that path. Our team has experience with these types of technologies, specifically at the grid scale. Those grid scale batteries are proven. For instance, Sumitomo has run a vanadium flow battery for 20 plus years at the utility scale, and we're partnering with a tier 1 firm that also has experience in engineering and manufacturing them. So our team has built utility scale vanadium flow batteries. We're partnering with a firm that has built utility scale vanadium flow batteries, and the technology is proven. And so with that, we're doing a qualification program with customers in which we give them a commercial unit. So this shipping container will be the power module. That's the engine, if you will, full of all the cells. Temporary tanks that we can put on site with no need for infrastructure. This will show them that we can fulfill all their power needs. And then with that, we will deploy projects. And so the projects will be full scale, similar to what you think of as a lithium ion installation or solar or wind. And so in this instance, it's a rendering of a full scale project. The engines are stackable in these shipping container modules. They're the Lego brick, if you will, that you build up to customer demand on the power side. And then the tanks are the storage aspect. And so that's the electrolyte that does the actual charge storage. And again, those can be sized independently of the power unit to provide the duration that the customer desires. So with that, Prometheus Hyperscale will be taking one of the qualification units, and then upon testing that and showing that we're able to fulfill their power needs at the data hall level. They want to lever up to 250 megawatt hours of installation. And so that's a very exciting thing for us because as we qualify with them, we move into projects at utility scale that are very large. Our team, as I had mentioned, has deep experience. So Bart Riley was the CTO and co-founder of A123. So A123, for those not familiar, was the pioneer of lithium iron phosphate. So every utility scale battery, all of the automotive types of batteries, the predominant lithium chemistry today is LFP. And that was pioneered by Bart. So they were the first people to do it, an MIT spinout. Three people started the company. It became the largest IPO in 2009 and is the predominant chemistry today. Meryl was the VP of engineering at Plug Power, the hydrogen company that's very large. She ran their engineering specifically for their stationary power. So shipping container products full of stacks, plumbing, pipes, sensors, essentially the exact same product architecture. It was just for splitting water for electrolyzing or full of fuel cells. So just a slightly different liquid, but essentially the exact same product at the megawatt class. And then Sequana was at DuPont, where she led Tyvek, along with $2 billion worth of P&L and a number of other verticals as well. She's done a couple $100 million in capital plant expansion. Lou was VP of operations at A123, and then also at Vionics afterwards, which I'll touch on in a second. But Vionics was a vanadium flow battery company at utility scale. And so Lou has deep experience both in manufacturing lithium ion. So from A123, he was the person who built the Korean factories. And then at Vionics, where he has experience with utility scale vanadium flow batteries. And then Mike, our CFO, has deep experience at a number of startups that have gone public. So with that, Bart brought with him Dave View as an advisor. So Dave was the CEO of A123, founder and CEO. And so he was with them for all 11 years as well. What's interesting with Dave is after pioneering LFP, he went on to found Vionics, which was the vanadium flow battery company at utility scale. So he has deep experience at that type of architecture. We've brought a number of people on who were a part of Vionics who have built utility scale vanadium flow batteries. He knew Ian Reed, who was CEO of Pfizer. He was not the right advisor for us, but Anthony Mataluna, who was a board member and number 2 at Pfizer, was the right advisor. He was in charge of global supply, which is chemical manufacturing. And so from him, we have a deep network of people and partners in the chemical manufacturing space. And then David Christian is from the utility side. He held a number of executive positions at Dominion, which is one of the largest utilities. So with that, because of the unique opportunity with a technology that exists at scale and is very mature, where we're just simply changing the electrolyte liquid and then making a few minor modifications based on the non-corrosivity, we can be significantly less capital intensive than other industrial hardware technology companies. And so that's a very, very unique opportunity. We're partnering with 2 firms that have deep experience in this. Columbia Tech is the design and manufacture company that Vionics used to build their vanadium flow batteries. So they have experience in this. And they have premier clients such as Amazon Robotics or Applied Materials. They do the semiconductor fabrication equipment. So deep experience in heavy industrial equipment, and specifically with vanadium flow batteries. And then ASM Chem is a leader in chemical manufacturing development to get our process ready for large-scale chemical manufacturing. So they did Paxlovid for Pfizer. So when the world was ending and a process needed to be built for large scale and high quality, ASM Chem was the partner chosen for Pfizer. And so they'll be helping us develop that high volume continuous process for manufacturing. Business model is a standard business model for this type of product. It's a direct sale for those that want to purchase, data centers, heavy industry. Customer owns the assets, manages the operations. We wrap it in a service wrapper. Or a tolling agreement or lease. Similar to solar and wind, utilities and IPPs look towards that, and then it's own and operate or potential sale to private equity for their owning and operating. Capital light, we aim to outsource manufacturing because this industry has become commoditized. and then patent protection is what carries us through. And then with that, what's unique is because the chemistry is unique, we have patent protection at many fences. From the molecules, their use in flow batteries, any derivatives of the molecules, the production process, and then the way that they interact with the battery, the materials of construction, any unique modifications for our chemistry, and then the software controls. And that's granted out to 2038 globally, as well as additional patents filed, which will extend that timeline. And so we have many layers. And so with that, we're at this unique moment in time where we've demonstrated with customers, and we're moving into that commercial phase to deliver customers our product in our billion-dollar pipeline. Happy to take any questions.
Okay, great. You touched a little bit on having a strong IP. Can you talk a little bit more about how that is defensible if you're using off-the-shelf elements?
Yep. So these, the electrolyte itself has never been used for any sort of flow battery application. And so we have granted patent protection over any derivative of our charge storage molecule for energy storage. And so with that, I came from pharma. That's sort of my background. So I was very aware of sort of the need to control any derivative of the type of molecule from a generics perspective. And so we have very strong granted protection over any derivative of our core electrolyte molecule, because nobody had ever used it for charge storage in a water-based system for flow battery application. And so we were able to get essentially it's similar to composition of matter type of patent. I don't know how familiar people are with the patent landscape, but that's granted in the US, and I'm happy to provide that to anybody who would like some further detail there.
Thank you. With all of these new battery solutions, do people really need oil and gas solutions anymore or in the future?
Yeah, so that's a good question. So it sort of becomes a philosophical question of how deep does renewables penetration get? And it essentially comes down to how low is the cost for storage, and then how low is the cost for incremental hours of storage. And so we believe that the market will likely move into the 24 to 36 hours of storage range, which will still need some oil and gas infrastructure. And so what will happen is the newest of the older gas assets will continue to be maintained and repaired to provide sort of that emergency backup for very corner case extreme weather events. So weather events such as 5 to 10 days of pure rain, so on and so forth, things that are sort of the once in a century types of weather events. And so there's a lot of modeling done, and it's probably around the 90% penetration level is where things will become uneconomical from a solar and storage perspective. But solar and storage is the cheapest form of generation if the storage aspect can be brought less than lithium from a duration perspective.
Callie?
And yes, please go ahead.
Jump in for a moment. I just wanted to maybe take this to a slightly higher level and make sure that the listeners understand kind of why the battery opportunity now. And the key is that the grid is this unique machine that always has to be in balance between the supply of power and the demand for power. At every instant in time, there needs to be a balanced supply and demand. And so two things have happened that have sort of changed the nature of that market. One of them is the supply side, which everyone is familiar with the penetration of renewables. And the main problem that renewables have is intermittency. So the sun doesn't always shine and the wind doesn't always blow. And so there are times when the renewables are generating huge amounts of power, even more power than would typically be demanded by users. And that power has to go somewhere in order for the grid to be in balance. So that's either turning off power that has very low cost to produce, or it's generating incremental demand. So what a battery can do is it can store power. It can essentially be that buffer that absorbs all that excess power that's being produced. And because price is driven by kind of the marginal cost of that last unit, if there's a lot of power being produced and limited demand, power prices drop precipitously. And so the owner of a battery can store power then at very cheap prices to be in a position to sell it later when prices are higher. So the battery can serve to as a supplement to demand. At the same time, we have this boom in demand that's coming for AI data centers. And the thing about AI data centers, unlike traditional clouds, is that the demand can have huge volatility in terms of peaks and troughs of demand in very short periods of time. And so that's a real problem for grid operators, because if all of a sudden you have a big spike in demand or a drop in demand, how are you going to balance the power on the grid? And that sort of volatility can lead to cascading blackouts, and in fact has led to cascading blackouts. And so the AI data centers actually create a demand for batteries, because batteries can be that buffer, offsetting either the spike or the drop in demand from AI data centers. So we're really at a time now where the type of power being generated and the demand for that power is much more volatile than it has been, frankly, over the history of the use of electricity. And that is what is causing the demand for batteries like ours to be a kind of a very much a today issue and going into the future.
Great, thank you. What is scalability at max?
At full scale production, probably hundreds of gigawatt hours. Organic chemistry can scale to exceptionally large scales very easily. It's actually everything around us, every plastic, every rubber, every coating, all of the paints, everything around us is organic chemistry from the oil and gas infrastructure. And so I think that's a really unique thing, is that we're leveraging what is the largest physical industry in the world, right? So the oil and gas industry is the largest physical producer of goods in the world. And with that, our feedstocks are scaled. There doesn't need to be a bringing up of that supply chain, if you will. And so from a supply side, it's as large as can possibly get.
Do you use vanadium, and if so, where do you source it?
So we do not. So that's the uniqueness for us, is we replace the vanadium. So it's the same type of battery as a vanadium flow battery. But what we do is we don't use vanadium. We use our proprietary organic molecule. And then that's dissolved into pH neutral water instead of sulfuric acid. And so by removing the vanadium, we remove a very large cost. And then I think maybe, as the question alludes to, 95% of the vanadium is owned by China and Russia. And so that's a very big geopolitical constraint. We don't use vanadium and can get around that geopolitical constraint. And then when you're not using sulfuric acid, which is the only liquid vanadium dissolves into, when you're using pH neutral water, we can replace all the componentry in the device with cheap plastics and rubbers instead of expensive corrosion resistant plastics and rubbers. And so we can drive cost out through that avenue as well. So it's the same device, but a different charge storage material and then a different liquid, which enables us to change all of the componentry for cheaper versions of the same componentry.
And where do you manufacture your batteries?
Yeah, so right now, Columbia Tech will be the manufacturer. That's their sweet spot, is that design and first manufacture. So they will be the small volume manufacturer as we move to market, but they can stand up to about 50 shipping containers a month. They can do about 2 a day. And so that's small in the global energy industry, but very much large enough for us to get to market. They then are a firm that hands that package to larger manufacturers. And so we have connections into the lithium ion industry through Bart and a number of other people on the team to outsource manufacture at a much larger scale, the shipping container types of products. The other thing is Columbia Tech's bigger brother is Jabil, who does a massive amount of these types of shipping container products. So Columbia Tech is the engineer and first manufacturer firm, and then that package will be transferred into a larger volume.
And do you have to pay Columbia a royalty?
No.
Thank you. So as someone that invests in alternative energy, um, how should they think about a comparison of this solution in regards to cost per kilowatt and margins?
Yeah, so I think I would need to better understand the question to truly answer it. So we are not a generation resource. So like a solar panel, we're going to be complementary. We're not a generation asset, we're a storage asset. And so there is a cost per kilowatt and then a cost per kilowatt hour, which is the duration of your storage aspect. And so happy to talk sort of in comparison to maybe lithium or vanadium. So we expect to be 2 times less expensive than lithium, both from a CapEx perspective and a levelized cost of storage, which is sort of, if you think of, there's the cost to purchase a car, and then there's the total lifetime cost of the car. So your miles per gallon, how expensive is the maintenance, so on and so forth. And then we expect to be significantly less than vanadium, 3 times less expensive than vanadium. So happy to answer that question maybe offline in a more
Sure.
detailed way if I understand it a little bit better.
Okay. What sea level does XL battery become comparable in price when compared to Lion batteries at megawatt level?
Yep. So interesting question. It's a little bit of an apples to oranges question. So we don't have a C rate because the duration is truly flexible. Right. So you build it's similar to a fuel cell if anybody's familiar with fuel cells. So the analogy is easiest to think of a car. There's an engine, that's the horsepower and the torque, and then the gas tank, which is how long you can drive the car for, how many miles. That's similar to a fuel cell where there's a stack of cells and then a hydrogen tank, and the hydrogen's consumed like a fuel. It flows into the cell and produces the power, and it's consumed like a fuel, and you refill it. That's very analogous to a car. We are more cyclable. It's not a fuel, it's a liquid that's charged and discharged. And so it's a true battery. But there is no C rate because C rate is essentially how long is the duration based on the various speeds. For us, you change the amount of chemistry by changing the tank size. Whereas like a lithium pack, you can't do that, right? A lithium pack is a singular constraint. So what I can say is there is no limit on the power side in terms of safety or operations. You could short the battery if you wanted to, and it's completely safe. But C rate is very much a lithium ion industry metric. And so I wouldn't compare us to that. At about 6 hours of duration is where we would cross the CapEx and levelized cost of storage of lithium. We are much more economical at 6 hours and beyond.
Thank you. And how fast can the system go from charge to discharge? And what time is required to get the system up and running from an off state?
Yeah, so that's a really good question. And so that's what we were doing. If I can find the slide. That's what we were doing with our demonstration unit. So charge to discharge is as fast as lithium ion. So essentially with this unit, we actually disconnected our cells and plugged in a lithium ion pack. And we ran the exact same tests on a lithium ion pack, and the results are essentially superimposable. And so our system is capable of doing everything lithium ion is capable. And so that's the easiest way to answer that question. That question can get very technical very quickly. But what I would say is we can do everything lithium ion can do. It's essentially superimposable.
Great, thank you. And what does a battery roughly cost, and what are the margins when at high volume?
Yeah, great question. So it's a little bit of a moving target on margins given all the tax credit kind of moving around. So I can talk about both with and without tax credits. So as a representative, Prometheus's 250 megawatt hour project would be roughly $60 million project. So an installation would be, for instance, for them would be roughly in the $60 million range. Margins with the tax credits would be somewhere in the 80s, high 80s in terms of percentage. Without tax credits, it would be in the mid 30s. And so it's still extremely high margins, even with subcontracting, right? And then as we vertically integrate, those margins can drive higher. We're choosing to stay capital light in our go-to-market plan. And so 35 with the subcontracting built in. And then we did, I think this might be interesting for people, we looked at what a project levels economics would look like as well, because one thing to understand as well is that there's both the battery margins, but then the project margins, right? So just like solar and wind, the project is developed and then sold, and then that's owned and operated by somebody who also produces a margin. So we partnered with a firm called Gaiascope, which is an AI dispatch algorithm that was operating 2.5 gigawatts of lithium ion storage in Texas. So they were operating storage. They were acquired by NG, actually. And so they will be running all of NG's lithium ion fleet. So one of the world's largest utilities. And when we looked at a 12-hour battery in Texas, so essentially what this did is every day there's a day ahead auction for the supply and demand side. So this algorithm would predict when prices are low, when prices are high in 15-minute increments day ahead. When do you charge the battery? By buying electricity. When do you discharge the battery? By selling electricity. And what we saw was for a 12-hour duration at our target metrics, with the tax credits, it was a 70% IRR unlevered with a payback period of 1.5 years on a 20-year asset. And even without the tax credits, the project level is exceptionally strong with a very fast payback period compared to the system lifetime. And so happy to sort of talk about that in more detail as well. But there's also margins on top from an own and operate aspect, which is an opportunity for Excel as well.
Is this still in design lab or in production?
So we are going through the commercial design right now with Columbia Tech, who has designed and manufactured utility scale vanadium flow batteries. So we're taking the data and engineering from the subscale demonstration, which was a fully integrated unit of chemistry, hardware, sensors, controls, software, BMS, everything, and moving that into commercial packaging. Essentially. So the 40-foot shipping container designed and engineered for high volume manufacturing. And so we're going through that development cycle of the commercial product, which Merrill has done a number of times on the megawatt class for this pretty much exact same type of architecture in concert with Columbia Tech, who has done it for vanadium utility scale batteries. And then once we have that design locked, we'll move into production.
And what do you see as your top few risks? Technology delays, escalation. Can you talk a little bit about your competition, and what contingency plans are you putting in place to address any of these, if any?
Yeah. So I think the unit has now been de-risked from a performance perspective, having been in the field as a fully integrated unit. So we don't necessarily see any technology risk. Now it's the commercial design in terms of packaging and price, right? It's getting that North Star, and what I can say is our North Star is price and quality, right? So a 20-year lifetime unit at a low cost, because in the electricity industry, cost is the driver. And so it's about moving through the development cycle with that North Star, which is not a technology risk. And then sort of with that from a competitor standpoint, I wouldn't necessarily think of competitors as other flow battery companies. It's more storage companies, right? So as a black box that takes in energy and gives back energy, there are a number of other technology types that are looking to do utility scale storage. And the challenge that they face is very low efficiency or high capital cost. And then additionally, when you look a little bit more towards the future, they max out at certain durations because of the way that the architecture works. So essentially, what's differentiating about flow batteries, and then specifically our flow battery, is the high efficiency. So as we move into electricity demand growth, there won't be excess electricity around. And so other comparable technologies from a sort of black box perspective have very low efficiencies, which means they waste 60 to 70% of the electricity that goes into the battery at the first stop on the value chain from generation to end user at the largest scale in the world. And so that drives project level economics, because you now have to buy a lot more electricity in order to sell. And so it puts those economics upside down, and it also adds a lot of cost to the grid level as a utility, if you're thinking from a utility perspective. So now you have to triple solar generation, you have to triple wind generation or gas generation, and that's a very expensive proposition. And so we believe we're positioned due to high efficiency and low cost to be the dominant technology.
And Tom, that efficiency or lack of efficiency in some of the other competitive technologies is why we were able to save that California $20 billion in investment, even while buying $28 billion worth of our batteries.
Yeah. Yeah. If your efficiency is very low, you'd have to overproduce solar and wind due to the waste.
The other thing that is a differentiator is response time. So some of the other technologies can't respond as quickly as we do. So we are really Tom likes to use the term a Swiss Army knife, but we can do everything that's required of batteries, whereas some of the other technologies out there can do one piece of the puzzle, but we can do it all.
Great. And is there a low temperature limit to the battery? What temperature does the electrolyte freeze?
Yeah, that's a really good question. So it's salt water. So it freezes around 28 Fahrenheit. I work in Fahrenheit units just due to where we are in the globe. So it freezes about 28 Fahrenheit. As a product, we're designing down to -20. And so for customers, there will just be a -20 limit on operations. And essentially, there's waste heat in any sort of energy storage system. This efficiency loss is heat. And so there's harvesting of waste heat from that aspect. And then if you're getting into really cold climates, tank infrastructure is generally buried. So even the oil and gas industry, so on and so forth, the tanks are buried. And that's a natural sort of insulation, if you will, and then in other sort of extreme cases, you can use heaters on the pipes, which is again typical. And what it is it's an out of spec efficiency hit for edge cases with customers that have sort of unique demands. If you're in northern Canada, Minnesota, like northern Minnesota, so on and so forth. But that would be the same for lithium ion as well, right?
Callie, you do your question sort of begs another question, which is what happens in hot environments, and for example, the Gulf states are looking to be a major hub for AI data centers. Temperatures obviously very hot there. Places in the southern part of the United States, very hot. And when you think about lithium as a potential alternative, lithium needs to be cooled. Flammability is a major issue. And so the hotter the environment that a lithium battery operates in, the more inefficient it becomes, the more energy has to be used for cooling. We, on the other hand, are happy to operate in warm climes. Probably the warmer the better is what I would say. So that's a consideration on both ends of the temperature spectrum.
Yeah, lithium ion really breaks down in the heat. So I think, as Jeffrey alluded to, lithium ion is also semi-disposable, right? Everybody has a phone or a laptop, things like that, and you know that your battery is just not the same 4 years later, 5 years later. The grid scale ones are oversized in order to sort of hide that fact. But when you get above 105, 110 degrees, that degradation becomes exponentially faster. And so that's the reason that they are air conditioned even in normal ambient temperatures, because the cells get, when they're driven that hard at the utility scale, they get that hot even in a normal temperature regime from an ambient perspective. So when you really get into hot climes, the air conditioning aspect can become a huge drain on their efficiency.
What is the timeline from beginning to end at commercial level?
So from launch to full scale. So
I believe so, yeah.
We see growth very similar to the oil and gas industry, right? It's been 120 years of growth from when sort of the first oil was found by Rockefeller out to now, with, I believe, most of the top 10 physical companies being oil and gas companies. Energy is the largest infrastructure market in the world, right? Global energy use is the largest scale. And so as this develops and grows, using oil and gas as our chemical feedstocks, it's just a transition of that into a new type of product that can essentially store renewables as opposed to be burned to provide energy. And so we really see, I mean, decades and decades and decades, a century of continued growth. We launch at around 500 megawatt hours. Because of the way organic chemistry scales, we're profitable at about 500 megawatt hours to a gigawatt hour. So very small in the global energy sort of regime. And then we see really unlimited growth from there.
Callie, I think our expectation is we will be delivering these qualification units to customers in 27, and we'll be delivering at commercial scale beginning in 28.
Great, thank you. And let's roll into some, financial questions. So, how much money have you spent from inception to today? Any outstanding debts?
Yeah, good question. So we're similar to how I talked about how we can be capital light going forward. We've been capital light to get to here because this technology exists. So as a battery company, we've deployed a field unit that's fully integrated for a total as a company of $20 million. So we've raised and spent $20 million to date to deliver a unit like this, and that is 10 times less than other industrial hardware technology companies, and we expect that going forward. We have no debts and no liabilities from that perspective. And then in terms of total cash to break even, we're expecting in the $50 to $75 million total realm due to the subcontracting and outsourced manufacturing model. So
And
again, 10 times less than other industrial hardware companies, and potentially 20 to 30 times less than other battery companies.
And any conversations with the current administration, any government funding, grants, anything?
Yeah, so we had NSF grant. We were, unfortunately, the grant was canceled. We were shortlisted and encouraged to apply the final application for an Office of Clean Energy Demonstrations grant, which was essentially for this commercial building block. And that program was canceled when the DOE budget was cut. But we were encouraged to apply, and we were down selected from 150 applications. So no current talks with this administration. However, batteries were in the bill that was just passed. Batteries were still what's the right term? They were not affected. The battery industry was not affected in terms of the tax credits or the development credits or anything like that. So those are still as they were. The solar and wind industry, those ITCs were shortened, but the battery industry was left. I think everybody understands that if we don't have storage, America will lose its ability to generate electricity and provide electricity in a stable and low-cost way.
Callie, but once again, a good question, and I would say that from my perspective, the door is open with regard to this administration, which is very focused on strategic minerals, on domestic supply chains. Our ability to offer a solution for storage where it is 100% U.S. source is something that we would like to be able to have conversations with. It's just to this point in time, our focus has been putting a pilot in the field that demonstrated that we could do everything that was necessary. With that having been done, we now move on to this next phase, which is on one hand, the commercialization, kind of bringing the pilot to commercial scale, and B, conversations about how we can be part of an American solution to the storage question.
Great, thank you very much. And kind of last question is, can you talk about your raise, what you're looking for?
Yep. So we are looking for 25 million to deploy these qualification units into customers' hands, and then unlock those larger contracts for commercial deployment at the hundreds of megawatt hour scale. And so that's what we're looking for, and that's the opportunity. Essentially, we have customers, we have this program to deliver them these units. When they perform as completely expected based on the previous demonstration that was into these customers' hands as well, then we move into full-scale projects.
Great. And for anyone that we didn't get to all of the questions, everyone out there has my email address. Please reach out to me. I can put you in touch with the team here, and they can give you a deeper dive, and really answer your questions a little bit more deeply. And so Thomas and Jeffrey, I want to turn it back over to you for any final words before we close out today.
Yeah, I think just to kind of follow up on that, I think we're at this inflection point where we've demonstrated the technology with these customers. We have a very big pipeline, which I'm happy to also go into detail on any follow-ups later as well. And just these two customers alone are $500 million worth of potential projects upon delivering these units. And so we're at this inflection point. It's a really unique opportunity given all of the pieces that come together to be very capital light while addressing this $4 trillion market. And I think it's a really exciting time.
Kelly, I'm gonna take advantage of being the chairman of the company for a last word, which is to say to your folks who you've introduced us to, I've stood in your shoes. I've been in the investment business for 40 plus years. I came to Excel in 2018, managing a family office, the Schwartz family office. It was such an exciting opportunity that I put together between myself and a couple of other family offices, the initial seed capital. We and my partners have participated in every round. There is no reason that Excel, that Excel can't be the next Tesla in the 2030s. It's a huge market. We have a moat around us from patent protection, and we're going to be a low-cost provider of a need that is going to be the biggest need of the next decade to go alongside the demand for AI. So I encourage you folks to consider joining with me and my partners in this project.
Thank you so much. Thank you, Thomas and Jeffrey. This was fascinating. And for the audience, thanks for joining, and please reach out to me to be connected. And I hope everyone has a great day.